All right, you little chemistry hooligans. We are going to continue on with our discussion of chemical reactions. And we're going to move on to the second part of this learning target. So what we've done so far is use patterns to identify types of reactions. Identifying our types of chemical reactions based on patterns. Now we're going to move on to this and part, which is predicting the products, right? Because again, what good is learning a scientific principle or theory if you can't use that to then make predictions? That's the usefulness of science, right? So let's start making some predictions. All right. So we've learned, right, that we have reactants, which are what we start with in a reaction, and our products are what we end up with in a reaction. Okay. And so when you're given both the reactants and the products, like you have been, right, what we've learned so far is how to identify what type of reaction that is. Right. Now, what if all I give you is reactants? Right? How can we then use stuff that we've already learned to then predict what might form as a result of putting those reactants together in the right circumstances, right? That's the next step. What will we actually produce when we mix certain reactants, if anything? Right? So we want to be able to predict the products of a reaction using patterns, right? And how will we do that? Right? We're going to use our knowledge that we've already learned about reaction types, right? Those patterns, A plus BC equals AC plus B, right? That kind of stuff, right? But we're also going to have to incorporate some of your knowledge of chemical names and formulas, right? So, for example, if I'm going to form, if I have a metal involved, right? If the metal is going to react, it's likely going to form some sort of ionic compound. If it does form an ionic compound, well, what's it likely to combine with? Metals form cations, which are positive. That means it's going to have to combine with something that forms anions, right? Okay, so there's some predictions we can make, right? We can integrate previous knowledge to then apply to this situation. So really, I'm not teaching you guys anything new here. I'm teaching you how to apply some of the stuff that we learned earlier. Okay, so our 5 reaction types for now are single replacement, double replacement, combination and or synthesis, right? Decomposition, and everybody's favorite, combustion. Right? So these are the 5 reaction types, right? And you guys have already written down in your notes, you should have from previous video lessons, already written down in your notes what the patterns look like for each of these 5, right? We have to have this in place. All right, so if all we know is the reactants, how can we then predict the products? Let's do an example. All right, so let's say I add some zinc metal, which is what you're seeing at the bottom of this beaker, to some hydrochloric acid in its aqueous form, right? So what will happen is we would likely see pretty soon after adding the zinc to the hydrochloric acid, or vice versa, we would start to see some bubbles form, right, around the zinc metal, bubbling up through that hydrochloric acid solution. Okay, now that's what we would see, but that doesn't really tell us what is forming, right? So we're going to rely on skeleton equations here to predict what ought to form. Now, so first of all, there's the 2 things we have to remember. One is what patterns tell me what type of reaction it is, and 2, what is likely to combine with what. So what I have is a metal. Zinc is a metal, right? We have hydrogen and chlorine, right? So zinc is reacting with something, right? Zinc is likely going to form an ion with a +2 charge, right? Now, zinc, if it's going to end up forming an ion, right, it has to combine with another ion or an anion. So we have a cation in the form of zinc, right? We need to pick which of these is going to be an anion. Now, I have taught you guys once upon a time that hydrogen generally does not form ionic compounds, or we're using that as a rule. Hydrogen doesn't form ionic compounds, right? And if it were to, it would actually end up being more positive than anything else, right? Now, one of the things we can do, now this is an oversimplification, but it's useful, right? We can treat hydrogen like a +1 in a lot of the reactions we do. Now, it is not actually a +1, okay? But we can pretend that it is. Okay? So let's just keep that in mind. It's one of the things we do in chemistry is we apply certain rules and models because they work for us, not because they represent actuality, but they allow us to usefully make predictions. So one of the things I want you guys to remember, we can treat hydrogen like a +1. Okay? We know that zinc, if it were to form an ion, would be a +2. Right? And that chlorine, if it were to form an ion, would be a -1. So we have to use what we've already learned about ionic compounds to predict what will form if zinc were to react with hydrochloric acid. Now, it's obviously reacting. We're forming those bubbles. That's one of those signs of a chemical reaction. Okay? So what is going to combine with what? So we've learned that cations will form with anions, or a plus needs to combine with a minus. Right? So I know what's likely to combine is zinc and chlorine on the other side. Now I can also use the patterns we learned, right? This looks like an A plus BC to me, right? And if you go back and look at your patterns, okay, we know that the A is going to replace one of those. All right? Now, if it's a cation, right, the cation would replace the cation. So in this case, the zinc would replace the hydrogen, right? Because zinc and hydrogen, in terms of ionic compounds, are not likely to form. Now, it does not mean, never mind. Hydrogen is weird. But anyways, what is zinc likely to combine with in this reaction? It is likely to combine with chlorine. All right, so we're going to, A is going to replace B. So I'm going to get AC plus B, right, in this reaction. So what I need to combine is zinc with chlorine. I'm going to go ZnCl2, and I'm going to form hydrogen gas. So the hydrogen gas makes sense because that's those little bubbles we see coming up out of that solution. Okay, zinc chloride is what's forming when zinc combines with chlorine. Now, what is it that you need to be able to do in this situation? Right, you need to look at the pattern. What does it look like on the left-hand side? So again, if you don't know what those products are going to be, all you have to do is look at what's on the reactant side to identify which pattern, right? And then you use that pattern to reconfigure the reactants into their new products. Okay? Now, we have to also make some decisions about, okay, well, if these are going to switch around, what is likely to combine with what, right? And then we can use our ionic compound rules to do that. Okay? Now, let's say, for example, I gave you this question, and instead of writing ZnCl2, let's say you write ZnCl and hydrogen, right? Now, the way I would treat that as your chemistry teacher is you understood part of this in that you were able to use the pattern to predict that zinc and chlorine would combine and that hydrogen would become the lone element, right? So I might give that a 3 out of 5, okay? Meaning you kind of got the gist of the idea, right? Now, how do we know that this is ZnCl2 and H2, right? That brings in some synthesis of stuff we learned in a previous unit, right? Zinc's a +2 and chlorine's a -1, right? We do our little crisscross method to write that formula correctly to make a neutral compound, right? And then H2, because it's one of those Brinkelhoff elements, right? Which means they are diatomic. Okay, now that's to get yourself up to that A standard, is to not only predict what will combine with what, but also to write the formulas correctly. Okay, now let's move forward. Let's do a couple more examples more quickly. So, predicting the products when you know the reactants. So we have aluminum sulfide and sodium oxide, right? Now, to me, this looks like an AB plus CD. That's a double replacement reaction, okay? So that means we're going to switch the A and the C. We'll switch with the B, right? Well, they're swap partners essentially. Whoops. Okay, now that also makes sense because we know that aluminum is a +3, sulfur is a -2, sodium is a +1, oxygen is a -2. I'm going to write that a little bit better here for us. All right, so the A, the aluminum, and the sodium will essentially swap places, right? So again, we can use that, that pattern, AB plus CD yields AD plus CB. That is our pattern. That is a double replacement pattern, right? Now, it helps to know the charges so that we can also correctly write the product. So I'm going to form aluminum oxide, which would look like this, Al2O3, and sodium sulfide, right? So notice the cation, positive always goes first, the anion goes second, right? And I'm also adding those little subscripts to make sure we create neutral compounds. But again, if you could at least tell me that aluminum and oxygen will combine and sodium and sulfur will combine, right? That gets you to a 3. You get the gist of the reaction pattern, right? I would just love to see you guys also correctly write the formulas. All right? All right, so let's do the next one. Let me pick a different color here because it's going to get messy. All right. So what I have here in this next one is just a single compound, right? So this looks like an AB, right? Now, what could happen to a single compound? Well, it could decompose, right? So this is going to be a decomposition reaction, in which case I would expect to split this compound up into its individual parts, mercury and oxygen gas, right? Because our pattern is A, B, the compound, splits up into A plus B. Now, that little triangle just means I had to apply some heat to make that happen. Next example, right? Here I have A plus B, right? So the only thing that could happen there is those two individual elements would have to combine. So that pattern matches our combination synthesis pattern. So what I'm going to do is I'm going to combine the iron with the oxygen. Now notice that Roman numeral 3, that means the iron is +3. We know oxygen is going to be a -2. So our formula will be Fe2O3. Okay? And last one, right? This looks like a hydrocarbon with oxygen, which we all know is going to be our favorite type of reaction, which is a combustion reaction. So we know, right? So I taught you guys this pattern. We've got the HN, the hydrocarbon plus oxygen is always going to produce carbon dioxide and water. Now that is a simplification, right? Now, so we got to recognize those combustion reactions because they're our easiest predictor. Every time we, in this class, so we combine a hydrocarbon with oxygen, we know that we're going to produce carbon dioxide and water. Now, those of you who may have once upon a time learned about balancing reaction, these are not balanced, right? And we are not going to worry about that until probably next week sometime. Okay, so you guys don't need to worry so much about balancing things. We will get to that. That is a very, very important thing. We have what's called the conservation of matter, right? But that is a lesson for a later day. All right, so you guys, what do you guys need to be able to do? Let's go all the way back here. Right? you need to be able to predict the products of a reaction using patterns, right? The patterns we know from reaction types and the patterns we learn from chemical names and formulas, right? The Chem Quest attached to today's lesson will give you lots and lots of practice with that. Adios.